Hello, my name is Tom Willemain. I'm one of the co-founders of Smart Software. Today we'll be talking about a particular common, widely used, and often effective forecasting technique called exponential smoothing. I want to talk about the basic thinking behind exponential smoothing, and after I do that, I'm going to show some math, so you might want to settle in and just go with it. We'll be talking about the various kinds of exponential smoothing. There are multiple variants of it. And we'll be talking about the trade-offs involved in tuning exponential smoothing so that it works best for a particular data set. And the approach to a different data set may require a different way of implementing the choices you make when you do exponential smoothing. So, first of all, what is it about? The essence of exponential smoothing is to say there is an underlying pattern in the data. Life covers that pattern with an overlay of noise, an irritating, misleading, zigzagging of data. And exponential smoothing tries to smooth out that noise to reveal the underlying pattern and make the necessary forecast obvious. So let's start in an ideal world where there is no noise and talk about the three types of data that we have exponential smoothing techniques to apply to. So we're going to have some variable that we want to forecast, and maybe we'll call it sales, and we have time, and in the ideal world, we have a data set that may look like that. We'll call that a level series. Or we may have a data set that looks like that. That's a trending variable. Or we may have one that looks like this, and that's seasonal. You can also, I guess, have a combination of these where it's seasonal but it's also trending. So those are the ideal types of data that we're imagining we've got. And we try to classify visually the data series we're working with into one of those types. And the forecast for each ideal type is itself obvious. If this is a level series and there is no noise and it's stuck at this value, that's the forecast. What else are you going to say? If it's this, trending, and the trend is unwavering, it just keeps going, then this would be the obvious forecast. And in the seasonal case, that would be the obvious forecast, or if there's a trend, we combine those, and we have trend and seasonality both. So that's the essence of the way we think about this problem. Very simple. You look for a pattern, and there are three basic patterns which might be combined. And once you've identified the pattern, the forecast is obvious. We make a leap of faith here that the future will be like the past. And all time series forecasting that starts at a graph like this and projects it out is implicitly making that assumption. Now something could happen here. Lightning could strike, and all of a sudden you might be down there or up here. But in the absence of knowledge about some special future event or absence of knowledge of a leading indicator, you might have seen our little tutorial on regression forecasting where we talk about knowing something about changes that are coming in the future. But if you just have this sort of data, you see the pattern, you make the obvious forecast. Now, these patterns are never visible in life because there's never a simple straight line with no noise attached. So what you'd really see in life for a level series might look like this. That's the way a level series would appear in real life. We would look at that and you say, yes, it's gnarly, It's zigging up and zigging down, it's jumping all over the place, but that gets classified as level. Because there's an underlying level, and superimposed on that is some random noise. So we really think of this as a combination of that plus something like this. You add those two together and you get a realistic level time series. So if this is the time series, obviously the forecast is going to be something like that. But is it here? Is it here? Is it here? Well, this one looks stupid and this one looks stupid because they don't look like they're anywhere near the middle of the data, right? If we can find the middle of the data, that's a pretty safe, sensible place to lay the forecast. How do you find the middle of the data? Well, if you look at each one, you can sort of eyeball it, and I sort of did here, and I say, okay, this one looks pretty good. This will be our forecast. But if you have 10,000 SKUs to work with, you're not going to enjoy looking at each one and making a manual decision about where the straight line should be. You have to automate that. And that's what the exponential smoothing algorithm does. Now, exponential smoothing is a child of the 1950s, which makes it slightly younger than I am. It was invented by Bob Brown back in the day when there was very little computation involved. And as you'll see, exponential smoothing makes very little demand on arithmetic and memory storage. So it was ideal. In fact, it was pressing the limits of what computers could do back in the early days of computing. It's still around, though, because it still is often the most accurate method of forecasting. It's simple, it's fast, and it's robust, meaning that it does well in lots of different kinds of situations. But the trick of exponential smoothing is it's an algorithm that replaces the human eye, and instead of looking at it and saying, here's the forecast, it will be running a line through here to constantly, on an updated basis, estimate where the middle of the action is. And the middle of the action, as estimated by exponential smoothing, may not at all, and usually isn't, where the last data point is. Because we're imagining that there's some invisible theoretical level which is corrupted by noise. And so we trust this orange line better than we trust that black line. We say the truth is covered up by the noise. We have to smooth out, average out the noise to expose the underlying level. And so the statistical forecast would be the one that projects out from where the algorithm thinks the middle of the data is at the end of the observed record. That's exponential smoothing. And likewise, the same thing happens here with the trending series. Let's just make that picture. A real-world trending series. Let's change it a little. Let's have it go down. So this could be a real-world trending series. You can see that there's an underlying, you can imagine there's an underlying straight line in there. Or maybe a line that is not quite straight. Maybe it starts to flatten out a little bit. So it's sort of dropping rapidly to the left of this line and less so to the right of that line. Well, what exponential smoothing is trying to do for us is expose what's underneath the noise, and it will try to discover this and then show that it sort of bends a little bit, and from here on it would project this line as a forecast. And finally, you can imagine the same sort of thing happening with the seasonal time series. There'll be an imaginary underlying simple pattern, a repetitive seasonal pattern. It's got an overlay of randomness on top of it. The randomness, essentially, from the point of view of forecasting, if you think of sports, it's the equivalent of head fakes and jukes. You don't want to go and follow every little zig and zag. You want to find the center of gravity of the opponent, tackle them. So you don't bite for the head fakes, you don't bite for the jukes. The exponential smoothing centers us on the middle of the data, exposes the underlying simple pattern, and uses that pattern to make the forecasts. So that's the philosophy. What we'll do next is think about what the math is, and exponential smoothing requires some judgments. It has knobs, one or two or three different knobs to adjust the sensitivity of the method to changes in the underlying pattern. And we'll talk about that trade-off, but that'll be changing a parameter in an equation, and the next pleasure we have is to think about the equations.